So in this topic we will be discussing on the introduction to design of water tank, the third part. Here we are going to see the behavior of rectangular water tanks and also the method for analysis of such tanks. So these are some points which we have to understand before going on to solve a rectangular design problem. Rectangular tanks are normally preferred for tanks with very small, small capacity compared to the circular tank, because the cost of shuttering is high in case of circular tanks with small capacity. But the exact analysis of the rectangular tank is quite difficult. The walls of the rectangular tank, it is subjected to bending moments both in horizontal as well as vertical direction. So if this is a rectangular tank, this tank, the upper portion will be subjected to horizontal bending and the lower portion will be subjected to vertical bending. We will see more detail on this later in this video. If the length of the wall is more in comparison to its height, then the vertical moment will be predominant and wall will bend just like a cantilever. So this is the case when the length of the wall is very high compared to its height, then such tanks will be subjected to, the wall will be subjected to cantilever bending, okay, or the vertical bending similar to cantilever bending. And if the height is large in comparison to its length, if the height is large comparison to its length, then the horizontal moment will be predominant and the wall will bend as if a thin slab supported on its edges. Okay. For intermediate condition, which is the most common type, there we have both horizontal and vertical bending in these rectangular tanks. The walls are also subjected to a direct pull exerted by the water pressure on some portion of the side walls. Suppose this is the tank, it's having two sides. This is one side and this is the other side. So if you are taking these two sides, okay, the water will exert a pressure on these two sides and there is a chance for bending like this, right? And due to this bending, these walls are actually exerting an axial pull on this side. Okay, that is what is called as the direct pull exerted by water pressure. The wall of a rectangular tank is thus subjected to both bending moment as well as a direct tension. So we can see both bending here. There will be some kind of bending both if the length to height ratio is in the intermediate condition, then we will be having both horizontal bending and vertical bending, and along with that we will be having this direct tension also. Okay. So there are different ways of analyzing a rectangular tank. Two methods are approximate analysis and exact analysis, which is based on elastic theory. In the approximate method, two cases are there. The first one is ratio of L by B. That means your length to width ratio, if it is less than 2, then here it is assumed that the bottom h, that is equal to h by 4 or 1 meter, whichever is more, will be subjected to cantilever bending, and the top h minus h portion will be subjected to horizontal bending along with direct tension. This is the case. So if the wall is L by B ratio is less than 2, then there will be both, in both the long and short walls, there will be both horizontal bending. This we have seen in the circular tank case also. This we have the horizontal bending in the top portion and cantilever bending in the bottom portion. The bottom portion h is equal to the total height by 4 or 1 meter, whichever is large. Okay. The second case is when your L by B ratio is greater than 2. This figure shows a tank like that when your length is by width ratio is greater than 2. So in this case, here it is assumed that long walls will bend like a cantilever, because this is a very long wall and this bends just like a cantilever, pure vertical bending only. And in the short wall, the bottom edge portion bends like a cantilever and the top edge minus edge portion bends horizontally, causing direct tension in long walls. So in case of short wall, there will be both horizontal bending and vertical bending, and due to this horizontal bending, it will be exerting some kind of axial pull in the long walls also. In this case, it is also assumed that the end to 1 meter width of the long wall contributes to pull or direct tension in the short wall, because the long wall is bending just like a cantilever, and it is assumed that the end 1 meter length of this long wall will be exerting the axial pull in case of short wall. So that is the two method in approximate method of analysis, two cases in approximate method of analysis. So we will be discussing more on the exact analysis, which is based on elastic theory, and we will be using the code for solving the problem. So note. So these are the points which we have to note. It is to be noted that the reinforcement for cantilever bending will be provided in the vertical direction. This we also see. This we have seen in the case of circular tank also, right? So it is provided in the vertical direction, and for the horizontal bending and direct pull, the reinforcement will be provided in the horizontal direction. So in the tank there will be vertical reinforcement and horizontal reinforcement. The vertical reinforcement will be taking the cantilever action. The horizontal reinforcement will be taking the horizontal bending and also the direct pull. Okay. For a section which is subjected to both horizontal bending and axial pull, this we have seen in case of rectangular tanks with the L by B ratio less than 2, and also for the short wall for the long wall case of L by B ratio greater than 2, right? When the section is subjected to horizontal bending and axial pull. So there the reinforcement need to be found in such a manner that the moment induced in the section by that axial pull acting at an eccentricity E from the section will be resisted by the moment of resistance offered by the sections. This we know in case of column design also we have seen something like this. So if you have a column with axial load and moment, this will be very much equivalent to a load acting at an eccentricity. So here in the case of a water tank, you have an axial pull, you have a moment. Okay, you have a horizontal moment acting, and also you have an axial pull. This is very much similar to an axial pull acting at an eccentricity E from the center of the section. So the line, so the moment due to this tensile force should be equal to the moment exerted by the or the moment of resistance of the section itself. So the moment of resistance of the section, we know it is T into A over T into JD, where J is the lever arm and all. The applied moment will be this P into the Z, the length, the distance from this line of action to the centroidal distance. Okay, so if that is one of the method by which we can find out the reinforcement for sections where you have axial pull and moment acting together, combined action. Okay. So we are coming to the exact method, and it is based on the elastic theory, and IS 3370 part 4 1967 give design tables for the calculation of bending moment and shear force. For square tanks wherein there is no rotation about the vertical edges, so when there is no rotation about the vertical edges, you can use table 1 to 3 of 3370 part 4. But in case of rectangular tanks, the fixed end moments calculated using table 1 to 3 will not be similar for adjacent wall panels. That means, if this is the adjacent panel A and B, the fixed end moments which we are calculating from table 1 to 3 will not be the same at this particular common vertical edge point. And the difference of this fixed end moment corresponds to unbalanced moment, and that tend to rotate the edges. So here we need to apply some modification, just like our moment distribution method, and so those modifications are introduced such that the end moments are identical on either side of the common edge. Table 5 and 6 gives the moment coefficient for rectangular tanks with different edge conditions. For a large number of ratios of B by A and C by A, where B is the larger dimension, C is the smaller dimension, both are the horizontal dimension, and A is the height of the tank. The values of the shear force along the vertical edges of a tank wall is required for the estimation of tension reinforcement due to direct tension. Table 7 and 8, we have seen the direct pull, right? We have seen the direct pull, and those direct pull are calculated from the tables from 7 and 8, which is the table for shear force calculation. For different edge condition, it is also based on different edge condition that we will be seeing more in detail while solving a problem. As per IS 3370 part 2 2009 clause 6.3b, when the tank wall is subjected to combined action of bending and direct tension, the criterion for safe design of wall thickness. So the criterion for safe wall thickness here it is sigma CBT dash divided by sigma CBT plus sigma CT dash divided by sigma CT, that should be less than or equal to 1. In circular case also we have seen the tensile stress. We know the permissible tensile stress, and we were calculating the tensile stress in concrete and checking with the permissible tensile stress. So here we have both horizontal bending and direct tension. So that is why we are using this formula. The numerator will be the calculated tensile stress due to bending, and denominator will be calculated tensile stress due to permissible tensile stress due to bending. The sigma CT dash means it is the calculated tensile stress in concrete due to direct tension, and the sigma CT will be the permissible value of direct tensile stress in concrete. Okay, thank you.